Alright, so before we get into Gay-Lussac's law of combining volumes as well as Avogadro's law, first we need to do some review of Science 10 concepts such as balancing chemical reactions here. So let's give these couple of examples a try here. So first off, we've got hydrogen reacting with oxygen to produce water vapor here. So the main idea with balancing reactions is what goes in must come out. So the same amount of hydrogens going in must come out. So let's take a look. Looks like we've got 2 hydrogens going in and then 2 hydrogens coming out. So that works. Okay, and what I like to do when balancing reactions is I actually like to make a little list instead of always keeping in my head how many of each element there is. So there's 2 going in, there's 2 coming out. Now with oxygen here, there's 2 going in. However, there's only 1 coming out, which is bad because what's going in is not coming out in the case of oxygen. Okay, so what we need to do is we need to use coefficients or the big numbers in front of molecules there in a chemical reaction in order to make sure the same amount of each element is going into a reaction is coming out. So what I'm going to do is I'm going to say to myself, okay, 1 times what is equal to 2? Well, obviously 1 multiplied by 2 is going to be equal to 2. So I'm going to take this number that I multiplied oxygen's amount by, and I'm going to put it in front of where oxygen is on the product side of the reaction. However, you do need to be aware that this 2 doesn't just affect oxygen, it also affects hydrogen. So now we also have hydrogen's amount multiplied by 2. So now on the product side we have 4 hydrogens. So now we need to ask ourselves, 2 times what is equal to 4? Well, 2 times 2. It's going to be equal to 4. Now I need to find where hydrogen is on the reactant side and put a 2 in front of it in order to reflect the changes that I made here. Okay. So now you can see that there's 4 hydrogens going in, 4 hydrogens coming out. 2 oxygens going in, 2 oxygen atoms coming out. So everything is balanced. This is done. Okay. Now we're going to do same process with this next example here. So I'm going to make a list, and for this particular reaction, since we have a fuel reacting with oxygen, which gives us carbon dioxide and water vapor, that's how you know that you have a combustion reaction, is something reacts with oxygen to give you carbon dioxide and water vapor. And since it's a combustion reaction, ultimately it doesn't really matter which order you balance your elements in. However, for combustion reactions, there is one way that does make it a bit easier, and the order is you balance your carbons first, then your hydrogens, and then you leave oxygen to the very end. Alright, so I'm looking here, and I've got 2 carbons on my reactant side, and I've got 1 carbon on my product side. For hydrogens, I have 6 on my reactant side, and I've got 2 on my product side. For oxygens, I have 2 on my reactant side, and on my product side, I've got 2 sources of oxygen, which makes this a little bit trickier. So I've got 2 oxygens here, plus 1 coming from here. So 2 plus 1, that's 3. Alright, so like I said, let's balance our carbons first. So I'm noticing, okay, my product side has the least amount of carbons, therefore I gotta start there. So 1 times 2 That's going to give us the 2 that we have over here. So then I locate where carbon is on the product side and I put a 2. Now that 2 doesn't just affect the carbon, it also affects oxygen. So I have 2 times 2 oxygen, so that's 4 oxygens in total coming from the 2 carbon dioxides, plus 1 more from the water vapor. So that's going to give me 5 oxygens. Okay, but I'm not going to worry about the oxygens just yet. Let's focus on hydrogens. So I got 6 on my reactant side and only 2 on my product side. So 2 times 3, that's going to give me 6. So I'm going to locate hydrogen on the product side, write a 3 in front of it. So that 3 doesn't just affect hydrogen, also affects oxygen. So from carbon dioxide, we have 4 oxygens from that. From the water vapor, we have 3 oxygens from that. So 4 plus 3, that's going to give us 7. Now the trick to make life easier with combustion reactions is notice how we have an odd amount of oxygens on our product side, and with our reactant side you're only ever going to get an even amount of oxygens because of this whole O2 business. Okay, so the way that you make your life easier is you take your number of oxygens that you have on the product side, and then the denominator is always going to be 2 because of this O2 part, because you have 2 atoms of oxygen here. Okay. Now, why does this work? Why does that give you 7 oxygens? Well, if you go, so let's write this off to the side, 7 over 2 times by 2. Notice we have 2 in the numerator and denominator, so that's how it equals 7. Okay. Now, for the concept that we're going to get into, you're going to want to have whole numbers for your coefficients. So what that means right now is this needs some working on because this is a fraction and not a whole number. But it's a fairly easy fix. All we need to do is we need to multiply every term or every chemical species here by 2. Why are we multiplying it by 2? Because of this denominator here. If we multiply everything by 2, our equation will still be balanced and we will get rid of this fraction. All right, so multiplying everything by 2, I'm going to have to write this off to the side here. That'll give us 2 C2H6. That'll give us 7 oxygens. 4 carbon dioxides, and then 6 water vapors. Okay. So this last example isn't exactly the prettiest, but since I don't have a whole lot of room to write this equation over again so that it's a bit neater, I kind of got to leave it like this. Okay, but our coefficients are 2 C2H6, 7 O2, 4 carbon dioxides, and 6 water vapors. All right, so bit of a typo here. This should be Gay-Lussac. Okay, so Gay-Lussac's law of combining volumes, as well as Avogadro's law, they operate off of a similar principle there. So Joseph Gay-Lussac, he was a French chemist and physicist, and he performed a bunch of experiments that was measuring the volumes of gases. Now, basically, doing all of these experiments, he came up with the law of combining volumes. And what it states is that the volumes of gases in a chemical reactions are always in whole number ratios. So that's why I said earlier here, why we couldn't have the fraction 7/2, because we want our coefficients to be whole numbers. And this is why I said that, because we need to have our coefficients in whole numbers, not fractions. Okay. Now, with Avogadro's theory, he proposed an explanation for the law of combining volumes, and what he said was equal volumes of gases at the same pressure and temperature contain an equal number of moles. So what this means is that the volume of gas is directly proportional to the number of moles of a gas present. Okay, now with this here, like this part underneath this chemical reaction is just trying to relate what the previous sentence is saying. So this sentence right here. So with our example here, we've got 2 moles of C8H18. So the amount of gas must relate to how much volume of said gas you have. That's what it's trying to say. Okay, and if you're wondering how this is going to work out in a calculation, we're going to get to this in a bit. Okay, but first we need to know that volume is not conserved. So what that means is that the total volume that you get if you add up the coefficients of the reactants is not going to equal the total volume of the products. However, we can use something called a mole ratio to help us predict the volume of gases either on the product side or on the reactant side. So the good news is these calculations are pretty simple. Okay, it's step 1, make sure you have a balanced chemical equation. That's why we took a bit of time to review how to balance chemical reactions. And then step 2, use the mole ratio to turn the volume of one gas into the volume of another gas. And it just depends on what gas the question's asking for. Okay, so first example here, the following gaseous reactants and products are at STP. So that's standard temperature and pressure. If you remember, standard temperature and pressure, that can be found on your Nelson periodic table. If you go to the second page, bottom right hand corner, STP, that's 0 degrees Celsius and 101.325 kilopascals. All right, so in the decomposition of ammonia gas, if 5 liters of nitrogen is produced, what volume of ammonia is required and what volume of hydrogen is produced? All right, so there's a couple of clues in these couple of sentences as to how to write the balanced chemical equation. Okay, so notice here that we've got the decomposition of ammonia gas. Ammonia is one of the chemicals that you should have memorized. Ammonia is just NH3. Since it's a gas, it's NH3 and the little G for gas afterwards. And since it's decomposing, a decomposition reaction is where you have some compound and it breaks apart into the elements that make it up. That's just a basic decomposition reaction. So what we have here, if ammonia is decomposing. We have NH3 as a gas. So there's our compound, our AB, in this little template that I gave us, and it breaks apart into its elements. So nitrogen and hydrogen. However, you got to remember Hofbrinkel. Okay, so Hofbrinkel is the acronym we use to help us remember all of the diatomic elements. So let me just write that out. So Hofbrinkel. Okay, so what this means is hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, all of those when they are by themselves, not in a compound, are going to be diatomic, or there's always going to be two of them when they are by themselves. So notice nitrogen and hydrogen on the product side, they're by themselves, they are diatomic elements, therefore we got to put 2s beside them. Now, if we go back to our periodic table here, and we just take a look at the states, it says gases are in red. Well, hydrogen, that symbol's red, so hydrogen is a gas at room temperature, okay, or at STP as this question has specified, as well as nitrogen is also going to be a gas. So what I'm going to do is I'm going to make sure to put states behind these. Whatever you do, do not forget to put states. You will lose marks if you forget that. Okay, so now that we got our skeleton equation here, now we can get to balancing. So I'll draw a little line under the arrow just to separate my reactants from my products, and I'm going to make a little list. And I'm going to repeat the exact same list on the other side of that line. Okay, so nitrogen, we have 1 coming in, 2 going out. We have 3 atoms of hydrogen going in and 2 coming out. All right, so I'm just arbitrarily going to start off with nitrogen here. So if I times this by 2, then I'll have the same amount going in and coming out. But that 2 doesn't just affect the nitrogen, it also affects the hydrogen. So we have 2 nitrogen atoms and 6 hydrogen atoms on our reactant side. Now, if we go to our product side, we only have 2 hydrogen atoms coming out. We need to also multiply this by 3 so that everything is balanced. Okay, so we have the same amount of nitrogen atoms going in and coming out, same for hydrogen, so this is completely balanced. Now, in the interest of space, I'm going to quickly erase this so that I have room to do my actual calculation here. All right. So the question says that we've got 5 liters of nitrogen produced. So what I'm going to do is I'm actually going to use my chemical equation just to organize what's given to me. Okay, what volume of ammonia is required and what volume of hydrogen is produced? So we don't know the volume of hydrogen, we don't know the volume of ammonia. So essentially there's 2 questions wrapped up in this one example here. So what I'm going to do is I'm going to start off with my given number, and I'm going to go times by fraction sign. Okay, so this is kind of going to be a little bit like unit analysis. Okay, and what our goal is we're going to convert our volume of nitrogen into volume of first ammonia, and then we'll do hydrogen. Okay, so nitrogen is in the top, so I'm going to put it in the bottom. And then I'm looking for, right now I'm looking for ammonia, so I'm going to put ammonia up top. Okay, so this part right here, this is called the mole ratio. And the numbers that we use in the mole ratio are going to come from the coefficients in our balanced chemical reaction. Okay, so if you look at nitrogen, there is no number written explicitly there. However, there is a little invisible one that, like, if a number isn't written in front of a chemical species, the number is not 0, or the coefficient is not 0, it's 1. Okay, so that's why I'm going to write a 1 here, and then the coefficient in front of ammonia is 2. So then I'm taking 5, multiplying it by 2, and then dividing it by 1, which is going to give us 10 liters of ammonia. Because if you treat nitrogen kind of like a unit, they cancel out. Okay, and what I've gone ahead and done is I've already put this in the correct amount of sigdigs, because 5 liters, that's 2 sigdigs, 10 liters, that's also 2 sigdigs. So that's done. And now we can move on to hydrogen, which I might have to write over here. So what I'm going to do is I'm going to start back with 5 liters of nitrogen. Why I recommend doing this is because if you were doing this question on a test and you had gotten this number wrong, and then you had used this number to figure out like how many liters of hydrogen you had, then you would have gotten the value for hydrogen wrong as well. So that's why I'm saying, as much as you can, use the values given to you in the question when you have a situation like this. So times by a fraction side. So nitrogen, and then we want hydrogen. So for nitrogen, as I said, coefficient in front of that is 1. Coefficient in front of hydrogen is 3. So 5 times 3 divided by 1, that's going to be 15. And I'm going to write it in the correct amount of sigdigs here. And there we go. Alright, next example. Gas barbecues burn propane, which is C3H8 gas, using oxygen in the air in a combustion reaction. If 5 liters of propane is burned, predict the volume of oxygen at the same temperature and pressure required for complete combustion. So same temperature and pressure, that part's just saying that you can use the mole ratio in order to convert the amount of propane to the amount of oxygen. Okay, so with what I said earlier about combustion reactions, you have a fuel, in this case propane, reacting with oxygen, and it always is going to give you carbon dioxide and water vapor if your fuel is a hydrocarbon. So if it's made out of carbon and hydrogen. Okay, so let's get writing that. C3H8 gas plus oxygen gives us carbon dioxide gas and water vapor. Okay, so the combustion reaction word, that's very important, and it tells you exactly what the products are and also what the other reactant is. Okay, but also this part also tells you what the second reactant is as well. Alright, so now let's balance this. So I'll write out my thought process here, but I'm going to have to erase it afterwards just because of space. So carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. So remember, for combustion reactions, it's always easiest to balance carbon first, then hydrogen, then oxygen. So we got 3 coming in, 1 coming out. 8 hydrogen atoms going in, 2 coming out. 2 oxygen atoms coming in, and 3 coming out. Okay. So let's multiply carbon by 3 to make that the same. Now this 3 doesn't just affect carbon, also affects oxygen. So we have 6 oxygens coming from here and then 1 coming from water vapor. So 6 plus 1, that's 7. Okay, now let's move on to hydrogens. So if I go 2 times 4, that'll give me 8. So 4 right there. Now that 4 doesn't just affect the hydrogens, it also affects the oxygen. So remember, coefficients affect everything in the compound behind it. Okay, so we got 4 oxygens here. So 6 plus 4, that's going to give us 10. All right, now 2 times 5, that's going to give us 10. So then our oxygens are now balanced out, and so is everything else. So now we can clean this up a little bit since we have a balanced chemical reaction. So remember, with these types of questions, step 1, get your balanced chemical reaction. Step 2, use your mole ratio to convert the volume of one substance to the volume of whatever substance that the question is asking you for. So in this case, because the question says we got 5 liters of propane, I'm going to write that right there. Is it 5.0? No, 5.00. All right. And then we're asked to figure out the volume of oxygen, so we don't know this one. Okay, so 5 liters of C3H8 go times by, so what you do is you write out your given number, then times by a fraction sign. We want to put the coefficient of C3H8 in the denominator so that these cancel out, and then we want to have oxygen. So the coefficient for oxygen is 5. The coefficient in front of propane is 1. So 5 times 5 divided by 1, that's going to be 25. And I want to make sure I have the appropriate amount of sigdigs. So this number right here has 3 sigdigs, so I'm going to go 25.0 because I want to keep the same value but make sure it has 3 sigdigs. Liters of O2. And that's that. For the next example, cars contain a catalytic converter which converts nitrogen monoxide, which is a pollutant, into nitrogen and water vapor by reacting with hydrogen. Okay, so that right there is telling us our chemical equation. Okay, so the converter converts nitrogen monoxide, so that's NO, and that's gas. And I'm going to leave a little bit of space because of the last part of the sentence. So it converts nitrogen monoxide into, so this is producing nitrogen and water vapor. So nitrogen is one of our diatomic elements, so I got to put N2. So remember, you can use Hofbrinkel to help you remember what the diatomic elements are. And then water vapor is H2O, gas. Okay, so converts nitrogen monoxide into nitrogen and water by reacting with, so reacting, that tells you this hydrogen is a reactant. So plus hydrogen, hydrogen's one of our diatomic elements. Okay, so due to space, I'll show you a little bit of a different way to balance reactions, but it's based off of the same principle that I have been using. I'm just not writing out everything that I'm doing. So starting with nitrogen, I've got 2 coming out and only 1 going in, so I'm going to write a 2 right there. Okay, now that 2 didn't just affect nitrogen, also affect oxygen. So I got 2 oxygens going in, 2 coming out. And then with hydrogens, I got 4 coming out, and that means I need to write a 2 right there to make it 4 going in for hydrogen atoms and then 4 coming out. Okay. So the catalytic converter removes 1.2 liters of nitrogen monoxide gas. So let's organize that. At SATP, so standard ambient temperature and pressure, you can find those conditions on your Nelson periodic table, but ultimately it doesn't really matter for this type of question. So SATP for every kilometer of driving. What volume of nitrogen gas is formed at the same temperature and pressure? So nitrogen gas, this is the one we have no clue. So let's write out our given times by a fraction sign. So now this is our mole ratio. So we want to cancel out nitrogen monoxide and we want to figure out nitrogen. So the coefficient for nitrogen monoxide is 2. Coefficient for nitrogen is 1. So 1.2 times by 1 divided by 2. Well, that's going to give us 0.60. I'm putting my answer in 2 sigdigs because my given number is in 2 sigdigs of nitrogen. There we go. Okay, last example here. Ammonia is produced from its elements. All right, so ammonia, that's the NH3, is produced. So that's telling you ammonia is a product, and we're going to assume it's a gas. It's produced from its elements. So we ask, okay, what makes up ammonia? Well, nitrogen and hydrogen make up ammonia. So then, because they're diatomic elements, I'm going to go N2 plus H2, both as a gas state. Okay, so predict the volume of hydrogen required to produce 1 megaliter of ammonia. So 1 megaliter, assuming same temperature and pressure. And then note 1 megaliter is equal to 1.0 times 10 to the power 6 liters, or in other words, 1 million liters. All right, so since we're asked to predict the volume of hydrogen, this is the one we don't know. So start off with the megaliters of ammonia and then do our mole ratio. So we want to cancel out ammonia, so I got to put it in the bottom because it's in the top. And then we want to figure out what hydrogen is, so I got to put that in the numerator. Okay, so I jumped the gun a little bit with this question here because notice how all of my coefficients in my chemical reaction are just 1. Okay, so that's why, and students often make this mistake, they'll just go, oh, 1 over 1, it's 1 megaliter. Okay, but that's wrong. Okay, what we need to do first is we need to balance our chemical equation. So we have 2 nitrogens going in, now we have 2 coming out. Now we have 6 hydrogens coming out, so we need 6 going in, and that's that. So we have 2 ammonia, 3 hydrogen for our coefficients. So 1 times 3 divided by 2, and that is going to give us 1.5 megaliters of hydrogen gas. And for my final answer, it's already in the correct amount of sigdigs, which is just 2, based off of my given number here. So this is done. One last point that I want to talk about is that the mole ratio, which is this part right here, which uses the coefficients from your balanced chemical reaction, it can only convert from one substance to a different substance if like the units you're using for your first substance are either volume, moles, or a concentration, which is usually moles per liter. So just one last time there, the mole ratio can only be used to convert from one substance to a different substance if the units you are using are either moles, volume, which is usually liters, but sometimes, like in this case, it's megaliters, and concentration, which most of the time for chemistry, 20 is going to be moles per liter.